First of all, the enzyme DNA helicase unwinds and separates the strands by breaking the hydrogen bonds between the complementary base pairs. Next, the enzyme DNA polymerase adds complementary DNA nucleotides. Notice that the newly synthesized strand complementary to the original strand is antiparallel. DNA polymerase is only able to add a nucleotide onto the 3' end of the previous nucleotide. As DNA helicase continues to unwind, the DNA polymerase continues to build the newly synthesized strand in the 5' to 3' direction, the same direction as the movement of the replication fork. As a result of this, we say that DNA replication on the leading strand takes place continuously.
To link individual nucleotides, a bond must form between the phosphate group of one and the sugar group of another. More specifically, the hydroxyl groups from the phosphate and the sugar combine to form a molecule of water, which is produced as the bond is formed. This process is known as dehydration synthesis because water is the byproduct. Now remember that with DNA, the sugar is deoxyribose. This name comes from the fact that one hydroxyl group has already lost its oxygen. If we replaced deoxyribose with dideoxyribose, both hydroxyl groups would be missing their oxygen. In this case, an adjacent nucleotide would be unable to bond because dehydration synthesis cannot occur. This sequence-stopping power of a dideoxynucleotide is at the core of dideoxy sequencing.